Hello, my name is Emily Ho, and today I will be presenting my final project for Intro to Materials. My topic of choice is on ablatives, typically used for rocketry. What is an ablative, and how does it relate back to materials? So ablatives, oh, sorry, my bad. What is an ablative, and how does it relate back to materials? So, ablative are a cost-effective solution to provide consistent cooling capabilities in a rocket engine. Some of its core functions is that it must withstand the mechanical stress of the pressure in the chamber and the shearing action of high velocity gas. I can go further into detail about what happens in the chamber. So in the chamber is where the magic happens. The fuel and the oxidizer reacts in the chamber to produce intense energy in order to propel the rocket into the air. What happens is that the temperature in a high performing engine becomes too much for the material that's made of. It goes higher than the melting temperature of most readily available metal alloys used for rocket engines. So that's where the ablative comes in to be the sacrificial cooling. Brings me to its next core function, which is that it must insulate and contain the hot combustion products within the chamber in order to protect the engine. When a rocket engine cannot handle the heat, it can actually cave in and explode. You do not want the rocket to explode. And that brings us to its final function is that it must shed away slowly or ablate when it's incapable of withstanding the heat any longer. So basically the the sacrificial part. For my experiment, I will be making a homemade ablative. It's low cost and non-hazardous ablative that's usually casted into a mold to create combustion chambers liners for amateur rocketry. These materials are actually commonly found and easily attainable compared to its alternatives. Luckily, I found all my supplies at Home Depot and Publix. So the materials that I will be working with are laminating epoxy, sodium bicarbonate, or rather known as baking soda, phenolic microballoons, but I couldn't find those in time because usually it's found online. So in its place, I will be using filler epoxy, which is a pretty well replacement. And it's also cheaper and more accessible. I'll be weighing them out. So it'll be 63.3% laminating epoxy, 31.7% baking soda, and 5% filler. Next slide, I'll be further explaining the properties and why I chose these materials. So for laminating epoxy, um, the epoxy serves as a binder and contributes to the structural integrity and the char layer. The epoxy resin has the benefit of being strong and tough. It does not char and pyrolyze in the same regenerative fashion like others. This helps the first function, which was to withstand the mechanical stress of the pressure in the chamber and the shearing action of high velocity gas. This also plays into a third function of ablating or shedding away when it's incapable of withstanding the heat. Next is the sodium bicarbonate or the baking soda. What does is that it will release water vapor and carbon dioxide as it thermally decomposes. This produces a film cooling effect that will help carry the heat away from the wall of the liner, protecting the engine. Uh, this carries out this carries out the second function mentioned earlier in the presentation, which was to insulate and contain hot combustion products within the chamber. Next is the filler. So instead of merely burning away, The phenolic chars puffs up into the carbon-rich layer. This layer acts as a semi-regenerative insulator. So as this char burns away, it produces a gas film that further helps insulate. This also carries out the second function along with baking soda and also the third function mentioned earlier. Next, I'll show you a video of, it's like a time lapse of how I did the experiment. Before starting the experiment, it's important to use the correct PPE. For this experiment, I only needed gloves. So I'll start playing. Oh, right. Let me start from the there. Right. Okay. I started off putting my cup with the saran wrap to make it easier to pull out so I can reuse the cup again. And then I used the scale to weigh out all my materials. First the baking soda, then the filler, and then the epoxy, which was equal parts of the resin and equal parts of the hardener. After preparing materials, I thoroughly mixed it up and poured it into a lined cup. And I let it sit out for an hour so that it can harden and take after its mold. Oh, I'll go into the next slide there. So this is the aftermath. I didn't possess a high performing engine to test it on, so I just used a lighter to show that it can handle heat. And what it looks like is kind of like a forbidden Reese's cup, but my friends told me it's like it looks like a forbidden brownie. But this is the aftermath, the product. It is hardened. It's like hard to touch and not easily mendable. It's very, it's also very tough as well. Uh, I'll go on to the next slide, which explains the composites of the ablative. So, ablatives are typically an advanced composite material, which is made of structural fibers and a matrix. When stiffened by the matrix, the fibers provide the necessary strength to withstand the mechanical stresses. The matrix acts like the glue to hold the fibers together and protects the fiber. The fiber protects, the fiber provides strength and stiffness to reinforce the matrix so that when the load is applied to the matrix, it transfers the load to the fiber. Like mentioned, the fiber is basically the strength factor, and then the matrix is the stiffness or toughness. It also provide a considerable portion of the insulative properties because it makes up of layers of fabric or fiber. It can pull away from the rest of the composite when the matrix is burned away. A typical composite material for ablative motors is silica phenolic. Other common materials are also carbon cloth phenolic, glass cloth phenolic, and as mentioned, the silica cloth phenolic. These are actually more efficient, effective than the homemade ablative that we make, but it's also more costly and the materials are harder to attain. And just a quick shout out, join SOAR, which is the Society of Aeronautics and Rocketry at USF. All majors and backgrounds are welcomed, and it's a great way to get hands-on experience.